Hello everyone, so I'm Sylvain Calmels and I will talk to you about damping behavior of short fiber reinforced plastics for the automotive NVH simulations. So I will at first briefly present e-Xstream Engineering, the company and our product, and then we will talk about NVH and the complexity brought by the reinforced material in this domain. Then I will talk about our very last enhancement in our product in Digimat 2016.0 for NVH, and we will follow the presentation with a demo of the usage of this last enhancement with Digimat product, and we will finish with a review of the results that we can obtain with this and how it influences the results for frequency response analysis mainly. So e-Xstream Engineering has been founded in 2003 and has been acquired 3.5 years ago by MSC Software company. It's a company 100% focused on advanced material modeling for multi-phases material. Our team is composed by 50 people, more than half is PhD in material engineering, and all the rest of the team is engineers. So we are developing Digimat, which is a leading multi-scale material modeling software today. Digimat is used by most of the material suppliers worldwide, and a big part of the OEM also in the automotive industry, and also tier ones. So Digimat, the interest of Digimat is that it's a very unique solution to work at the material engineering level as well as the structural engineering level for all the type of microstructures that you could meet when using multi-phases material. So it can be short fiber reinforced plastic, it can be long fiber, hybrid composite, UD, woven, braided, mucel. As soon as you have a multi-phase material, even if it's only about air inclusion, it makes sense to use our Digimat, and you can do this with one single tool. So the principle of the multi-scale material modeling technology embedded in Digimat is to work with the constituent properties of the materials and the microstructure organizations. So these are the inputs of the material model that we are creating. It contains basically the properties of the material for the matrix, the property of the material for the reinforcement, whatever it is, short or long or continuous fiber, and also the microstructure description, so how the fiber or the reinforcements are organized in the matrix, the shape of the reinforcement, let's say for short fiber, the aspect ratio, for example, of course the volume fraction. All of this is taken by Digimat, and through an homogenization technique, it helps to predict the nonlinear and isotropic behavior at the macro scale level for every type of fiber orientation. For example, if we talk about short fiber material. So you can work with such technology in two ways. The first way is by using the mill-field homogenization technique. This way is used when you want to run structural FEA with any solver of the market with one of our material model. And you can work also for pure material engineering works with direct analysis method, where we build RVE, we mesh RVE with any kind of microstructure, and we can compute RV analysis to help understanding the deep behavior of the multiphases materials. So today we are following the motivation and the challenge of our customer in the automotive industry. So of course, I mean, everyone is aware that there is a big chase for lightweighting in the automotive industry. This is mainly driven by the OEM's customer interest themselves for fuel consumption and vehicle performance, of course. but also the well-known environmental constraints. So all these interests pull the innovation for lightweighting, and then it pulls the growing usage of composites and reinforced plastics in the automotive, in the new vehicle structures. But these new materials are much more complex than the metal which was mostly used before, and all this complexity bring with them the obligation at first to use a conservative method, and it can enlarge also the development time, and in the end it will enlarge the development process and or lead to over-design, mean useless added mass or non-optimal usage of the material in the final parts. So this means that the industry today is looking for new solutions which are more accurate and able to take into account the specificity of this multi-phases material by comparison to metals. So today, Digimat allows to really bridge the gap between the manufacturing process and the final performance of the structural parts, and this for any type of microstructure. So it means you've got some example here for woven, for braided or DFC. This can be used also with all the solvers, the FE solvers of the market, and for any kind of performance that you would like to target in the end, crash, static, strain, or stiffness, but also, and this will be the topic today, NVH. So very briefly, when we talk about NVH, so noise, vibration, and harshness, we talk about the performance which aim is to master the passenger comfort regarding the noise emission from the car, from the engine, well, from all the vehicle. You've got basically two sources of noise transmission through the structure. Basically the solidian one and the aerian one. We will focus today on how we improve the prediction of the solidian way of transmission. There is basically two levels of application for FEA, for design. The first one is at component level, so there is works, of course, at the engine level, but even in the engine, it can be some work at the component for cam cover. You know that today there are some OEM which are doing cam covers made in reinforced plastics already. And of course, the second level is the body in white and the full vehicle, where we, in the end, need to evaluate the level of noise at passenger ears. So here, plastic usage has a particular interest. We always talk about metal to plastic replacement for lightweighting reason, but when it comes to NVH, lightweighting is not the only reason. It can be also chosen in replacement of metal for its better dumping behavior, and reinforced plastics helps to reach better targets in terms of NVH performance. So today, this is a basic draw of the usual numerical workflow which is followed for NVH FEA. So here it's a case when the user is using Nastran, of course. Nastran is well known for its capability for NVH analysis. So mainly, whatever we talk about doing analysis at the body in white level or in components, it starts always with Nastran Sol 103, some model analysis. We need always to evaluate the model basis of the parts or the vehicle. So the physical property which needs to be correctly predicted here are stiffness and mass. And we target eigenfrequencies often at this level, so it can be on components. For example, for on seats or on dashboard beam, on engine mounts, cam cover, or something else. Following this, we are doing frequency response analysis, really to evaluate the vibrational and the dynamic response which is provided by the part or the vehicle. At this level, the equation change a little bit because we don't only care about the stiffness behavior of the material and the structure, but also about its damping behavior. And here we add there is a new output compared to model basis, which is of high interest. It's the peak values in acceleration response. And to evaluate correctly peak values in acceleration response, we need to predict correctly the damping behavior of the material. And in the case of multifaces material, it's really much more complicated than for metal, where an isotopic and homogeneous assumption was used for years and worked quite well. Then once all these vibration analyses are done, it's possible to do the acoustic response and to calculate the level of decibel at passenger airs. So today, what are the modelization challenge when we talk about doing frequency response analysis? So I focus mainly on this one because, as I mentioned, it deals not only with stiffness but also with damping. So here the complexity which is brought by reinforced plastic is that we have to take into account the local anisotropy, which is due to the heterogeneity in the fiber orientation distribution through the part, which can vary a lot. Even with a single geometry, if you change the injection parameter, the positioning of gates, you change the fiber orientation distribution, and then you change the local anisotropy of stiffness. You've got also to take into account, in the ideal way, the frequency dependency of stiffness also. So this remains to take into account the viscoelasticity of the material. If you are not accurate on stiffness prediction, the direct effect is that you have error in the identification of the modal basis at first, but also in the identification of the excited frequencies when you do frequency response. So these are the first level of error that you can do by not doing multi-scale analysis. It's error on stiffness. Now, regarding damping, you've got something quite similar in the fact that the damping behavior of a reinforced plastic material is also highly driven by the local fiber organization. It means that locally you've got a damping behavior which is anisotropic and dependent on the fiber orientation. And the damping is also highly frequency dependent, perhaps even more than stiffness. And all of this today is rarely taken into account, at least the anisotropy and the link to fiber orientation for damping is really never taken into account because there is nothing to do it. And frequency dependency can be taken into account, but as it can be done only in an homogeneous way, it's even not accurate. And then the error here is worse than the error that we can do with a stiffness homogeneous law. Here the error is that we won't identify correctly the acceleration peaks, the local acceleration peaks in the structure, and then we won't identify correctly the noise levels, which means that in the end you will obtain a design which is purely wrong. And you will be aware of that when you will do the first physical testing. It means that you will have to do additional design iteration, so loss of time, loss of money, and also in the end there is a big chance that you do over design and to correct the error of simulation. In fact. So what are the enhancements in Digimat 2016 which might help you to avoid this kind of error and risk in your design processes? So I will go straight forward to the point. Basically, what has been improved today is that you can use a viscoelastic, at first you can use a viscoelastic Digimat material model. So By Digimat material model, I mean a material model which is able to capture locally the effect of fiber orientation on the material properties, means stiffness and damping. So you can use such material with a harmonic analysis with Mark and Abacus. And you can also use a viscoelastic material model, Digimat material model, with the Nastran Sol 1XX solution, so the Sol 103, of course, but also the Sol 108 and the Sol 111, which are really much more interesting in this case. So here it means that Digimat will help to perform Nastran computations with damping properties corresponding to the viscoelastic properties calculated. It can be calculated at a given frequency if you choose to target one frequency, for example. But it can also be done, the frequency response analysis can also be done with a full frequency dependency of the viscoelastic property. It means that for each frequency of interest along the frequency range of the frequency response analysis, Digimat will calculate and provide to Nastran the correct anisotropic stiffness and damping behavior for the given frequency. And this is a huge improvement compared to what was possible until now with reinforced plastic for frequency response analysis. So it means that today we with Nastran, but not only with Nastran, also with Abacus 6.14, at least you can take the benefit of take into account the local anisotropy and the frequency dependency, both for stiffness and damping when you are using Digimat, which is not possible if you try to run a frequency response analysis in a standalone version of the calculation, so with Nastran alone or Abacus 6.14 alone. So I will now show you sorry. I will now show you how we can set up such a calculation with Digimat today. The example I will use is the example of a frequency response analysis, driving point analysis made on a full front roof beam of a car. This one is a version which is made with a PA6GF30 reinforced plastics with a thickness of 3 millimeters. We will use Digimat viscoelastic material model. So you've got on the right hand upside of the slide the view of the behavior of this material. So it's the curves are the axial response of the material under various strain rate. So it's a viscoelastic material model, and we will show the effect of the fiber orientation also, because I will show you the result that we can obtain when using two different fiber orientation fields, which correspond to two different gate positioning for the injection process. So, to generate such material model, you have to use, of course, Digimat, and you have to open Digimat-RP. I have prepared already the files, of course. So for those who knows Digimat-RP already, it will be nothing very new at this level. So you have to load your isotropic version of your job. So here we've got a PDF file, an Nastran file containing the frequency response analysis with all the details of inputs, of course, but outputs also, and an isotropic material model here. So I load it into RP. Here we are. So it's a shell mesh. I will now load a Digimat, a viscoelastic Digimat material model. Here, we've got it. So you see that we've got the constituent properties. So we've got a material for the matrix here, which is a viscoelastic material. So you've got here the terms of the Prony series, which describes this viscoelastic behavior, and we've got material for the fillers, the inclusions, here, which is glass and is a basic elastic isotopic material, because we consider here in this case that the viscoelasticity property of the final composite is mainly brought by the viscoelasticity of the polymer. Now we have to define microstructure. It means in this case we have to define the fiber orientation field. So you've got several choices. I will just briefly show how we can set up fiber orientation estimation, because behind Digimat-RP you have the possibility to run a fiber estimation with moldex 3D. So this is a little bit out of the webinar today, but I wanted to just to show this quickly. So you can calculate directly from RP through moldex 3D behind. You can calculate an estimation of the fiber orientation following a basic assumption that you can do on for the injection process. So you have a library of material for the rheological properties. So here I will use a PA6 GF30 material here, and you can define also some gate positions. So here we got the part, and you can position, for example, one gate here. You can add a second one here. You can play on the diameter of the gate. Another one here. Well, you see that it's really quick to set up. And once you have defined the positioning of your gate, you can run directly a fiber estimation here, and you've got moldex 3D which will run behind and helps to have very quickly an estimation of the fiber orientation tensor distribution in your part. This new capability also helps a lot to accelerate the design iteration by being able to adapt and to predict quickly a fiber orientation estimation for each new design iteration that you can do. So I won't run it because, well, we have to do it, but I did it already, and I will load the project that I did before with that, and we will progress further on the setup of our frequency response analysis. So here we are. So you see it's the same part, but it's at the end of the fiber orientation estimation here, and it has been already mapped on the structural mesh. It has been already mapped directly in Digimat-RP, of course. I mean, when the calculation of the fiber estimation is done, you recover the result directly in RP, and you can map it directly in RP on your structural mesh here. So once the model is ready, here we have our structural mesh. We've got the viscoelastic material, we've got the fiber orientation estimation mapped on the structural mesh, so we can submit the analysis. So you choose the run folder, you confirm, and here you've got the choice between two possibilities. Digimat-RP has detected automatically that the job is a frequency response analysis with Nastran, and it proposes two options because it has detected also that you work with a viscoelastic material model. You've got the choice between select a frequency. So, for example, you can select 100 Hertz. If you select this option, Digimat will calculate the anisotropic and stiffness and damping on the whole model, depending on the local fiber orientation, and will generate the new Nastran input deck, depending on the data calculated at this frequency. If you choose a full frequency dependence, then Digimat will calculate a set of Nastran input decks in which you will have all the stiffness and the damping material behavior, which will be calculated for each frequency of interest along the frequency analysis. So in my case, I will do it now. In my case, it's frequency analysis which is between 1 and 300 Hertz with a step of 1 Hertz. So it means that here Digimat will calculate the stiffness and damping properties each Hertz from 1 to 300 Hertz, and behind this we will be able to calculate all the Nastran analysis for each frequency, and in the end we will recover the results for the full frequency analysis. So you will see quickly what is done by Digimat-RP. Here it's generating the couplet analysis. So here it is. So you see that we've got a set of BDF file. We've got 300 BDF file here. And in each of them will be calculated the response for one given frequency, taken into account the stiffness and the damping behavior for this given frequency. And in the end of the calculation, all the results will be merged into one unique output file, and then you will be able easily to post-process the acceleration response with the full frequency dependence in the end. So I won't run all of this, but we will go directly to the results that we can obtain. So here is the kind of result that we obtain on this roof beam. So here we've got 3 curves on the screen. The yellow one has been made with an isotropic and homogeneous material model, which is used if you don't use multi-scale techniques. Basically, I have calculated the axial stiffness and I applied a factor of 0.6 on it. And I've used a conservative definition of damping, which is still homogeneous here, but frequency dependent still, as it was possible. And the green and the blue curves are the response I have obtained with this last enhancement in Digimat with the full frequency dependent capability for the 2 gate positioning that I shown to you earlier. So you see that at first Digimat is able to predict the different behavior for the final structure depending on the injection process parameter that you could decide to use. So depending on the location and the number of gates that you can choose to put on your mold, you will get different fiber orientation through your part. Digimat is able to capture the effect of this and to calculate the correct behavior for the final part. If you use an isotopic method, of course, there is absolutely no link to injection process, so you've got one behavior which is only driven by the geometry, but not by the injection process, which does not make sense when we talk about reinforced plastics, of course. So here you see that you can have a huge difference in the frequencies that you can identify, the excited frequencies that you can identify. But what is more important is that you can have very big differences in the acceleration levels that you can identify with isotopic or with Digimat capability. Even if we talk only about Digimat, here you see that by choosing different gate positioning, you can change the response of the analysis, you can change the acceleration peaks that you obtain in the end, and then change the noise, the prediction of noise for the final performance of the full vehicle. On this graph, we have 3 calculations which has been made all with Digimat 2016. The first one is the same that we have seen on the, so it's the red dotted one. The red dotted one is the same that we have seen on the slide before, so it's the calculation with the gate positioning 1 with a full frequency dependency for stiffness and damping. And we've got also 2 other curves with the response calculated at one given frequency. So for the yellow curve, it has been calculated with data at 100 Hz. And for the gray curve, it has been calculated with properties at 300 Hz. And what is interesting here is that you can see that the full frequency dependency analysis match with the 100 Hz response around 100 Hz. And it matches with the 300 Hz response around 300 Hz. So it means that, I mean, at the beginning, when you don't know exactly, if you don't know exactly which frequencies will be excited, by running a full frequency dependent analysis, you will ensure that you will match correctly the correct behavior, whatever will be the excited frequencies in the end. If you choose to work with a fixed frequency to calculate the stiffness and damping, it means that you will have to run a first analysis to identify the acceleration peaks, and then you will have to run a new one and request to Digimat to calculate the stiffness and damping for this given frequency. But this means also that if you have several peaks, at several different frequencies, you won't be able to match correctly all the peaks. You will have to target perhaps the highest one, which is still valuable. I mean. So, in summary, we have seen that the biggest challenge today for NVH simulation, when the user wants to use reinforced plastic material in its part, is to deal with the complexity of the material behavior regarding especially its dependency both to the fiber orientation and to the frequency dependency. Not taken that into account will lead for sure to correlation problem between simulation and testing, and in the end, you know, like me, that the correct response is in the physical test. So it means that simulation will be or useless or will lead to over-design, or well, it's clearly not a correct way to proceed to use isotopic material when it's about reinforced plastics for NVH. So we have now in Digimat 2016 new enhancements, which is very interesting, I think, and which will help to improve clearly the accuracy of NVH prediction by using viscoelastic multi-scale material models directly in the simulations. And this will help for sure to optimize the design iteration loops. They will be executed with more confidence, and in the end, it will help you to reach better targets in terms of lightweighting, but also in terms of pure NVH performances.